So, welcome everyone to Guided Study Group Math 141 of week 15. So, this is the last Guided Study Group for Math 141 this semester and also the last piece of material. So, next week I'm gonna run like a last minute final exam review. It's kind of like you get like put everything together for anyone that hasn't had a chance to review for next week exam yet, and then we're gonna call it a semester. So we're gonna go to 10.3 and 10.4 today. So basically, as I kind of like briefly mentioned last week, we're gonna work on polar coordinates this week. And so there's something we're gonna start with polar coordinate system. So it's the 2D coordinate system, each point denoted by r theta, with r be the distance from the origin, kind of like we're similar to it in the way we call it the radius. Theta be the counterclockwise angle required to reach the zero array. So say here, like so this is r and this is theta. So something to relate it, if we draw a graph, say negative r theta, so r is negative, so this is gonna be, redraw it. So say if you have negative r with a theta this way, then theta, give me a second, and negative r is here with an angle theta. So this is angle theta, and this is negative r. And this one is going to be the exact same thing with having the radius r, but with the angle of theta plus pi. So if you draw like negative r, it will give you the exact same thing. So that is what I have for this part. Okay, so some connections. Oh yeah, a point can have multiple representations in polar coordinate system, and this is because of this one. Just like a difference of pi, and maybe even if you expand it into 2 pi, 3 pi, it will give us a new representation. And so a point can have multiple representation in the coordinate system, polar coordinate system. There's also something related between polar and coordinate Cartesian system, which is x is r cosine theta, y is r sine theta, and this is because when you draw the graph, say you have this line, x is clearly your r multiplied cosine, y is clearly x multiplied sine, r multiplied sine, and tangent theta is just y over x. That's cosine over cosine. And then you have x squared plus y squared is going to equal r squared. We also have polar curves. It's going to be written as r equal a function of theta. And how do we know what graph it is? As you can see in your lecture notes, you have a lot of graphs like sine theta, cosine theta, sine 2 theta, cosine 2 theta, and so on and so forth. The way that we're gonna do it, say if you were given a list of like a lot of graphs and asked to choose, you're gonna choose it based on the frequency. So say if it's theta or 2 theta, you're gonna see like how many times does that graph repeat on the cycle, say from 0 to 2 pi. Or you can check the initial points, like you plug in 0, pi over 2, pi over 4, pi over 3, pi over 6, so on and so forth, just to check, see that point matches what you're looking for. If they all matches, it's really likely that it's the graph that you're looking for. And also maybe use a table, just kind of like keep things neat, write like all these values in a table to keep track of it and not make it too long. Or in another way, you can also learn it by remember from lecture notes. But I wouldn't say that's the um, recommended method because it's way too. I mean, math is not about remembering, but as long as you do as many practice as you can and it just get into your instinct, that'll be best to apply. We also have symmetric of graphs, which is another way that to help you to find which graph is which, but I find this one kind of not very commonly used among students. So I have a polar graph is if it's unchanged, if you replace theta with negative theta, it's symmetric about a polar axis. If you replace r unchanged by replacing r with negative r, it's symmetric about a pole. And if it's unchanged if you replace theta with pi minus theta, it's symmetric about the line theta equal pi over 2, which is this is the polar axis. So this is the polar axis. This is polar axis. This is the line of theta equal pi over 2 and the pole. So these are the three things that it can be symmetric about. Some problems that you might be asked in these questions: convert a point from polar coordinates to Cartesian coordinates, and this one is using the link that we have before, connections between polar and Cartesian coordinates. Then we might be asked to find a Cartesian coordinate or equation for a polar one. Then know the shape of the common graphs, and maybe you might be able to be asked to identify which is which in the exam. And so yeah, make a list, note the train, kind of like give you some hint about like how you're gonna figure these things out. So let's go to the first example. I feel like I have quite a couple of examples here. So example 1 is sketch the curve r equal 3 sine 3 theta. And so the way that I'm gonna do it is I'm gonna put all of the special point here, and that's how I usually gonna do it in the table, and that just kind of keep me track. And also in the lecture notes, if you notice, you would already know the shape of the thing is gonna look like this, but you don't know what's the first point of that and where does it start from creating these loop. So let's put it 0, pi over 6, pi over 3, pi over 2, pi over 2 pi over 3, 5 pi over 6, pi. And we're just going to repeat it. So it's going to give us, say, first is 0. 3 times pi over 2 is 3. 3 pi over 2, put in negative 3. 0 again. This is also 0. 5 pi over 6, if you put in just 5 pi over 2, which is essentially pi. So the graph we have here. So we have from the first point is at 0. The second point is at, so let me graph out what is the line of pi over 6. And then the line of pi over 3. Okay, so pi over 6 is 3. So this is the point. Pi over 3 is again 0. Pi over 2 is negative 3. So this is the angle of pi over 2, but the radius is negative 3. So you put 1, 2, 3. Then you have 0 again. And then 5 pi over 6 is 3. So 5 pi over 6 is this angle. And so you have 1, 2, 3. So, and then it's 0 again. So you can see that it's going to create a loop on this side before a loop that's here and a loop there. So this is the way we're going to do it. Yep. If you want, you can expand in more angles. I would say the thing what I'm missing here is pi over 3 is here. So somehow it's so maybe put in pi over 4. Let's see what it gives us. It's a bit odd over there, but you put in pi over 4, what you have is 3 pi sine of 3 pi over 4, which is against the square root of 2 over 2. Yeah, this can be a quite odd number. It's not really helpful. Let's say pi over 12. Pi over 12, when you put it in, yeah, not really helpful. But from here, you can kind of like identify the fact that if you go any further, it's going to repeat itself again. So that's kind of, if you continue to expand, I would say like 5 pi over 3 and so on and so on. That will give you kind of the same graph. So let's call it the graph, and then let's go to example 2. Sketch the curve r equal cosecant theta. So in this case, if you ask to graph like cosine and sine, that usually is the easier one. But if you ask to graph something related to anything that's not sine and cosine, like cotangent, cosecant, secant, tangent, all of that, the way that I usually approach this is that I'll put it back into a Cartesian equation, and that's perfectly fine because you can have more than one representation for a curve, and it can be on either Cartesian or polar. And so, I mean, one of the things we also need to notice is not every single polar curve will have a Cartesian equation, but it doesn't hurt trying. So cosecant is 1 over sine theta. In this case, you have r sine theta is 1, and that is equal y equal to 1. So instead of a very complicated graph, it turns out to be really easy if you put it in Cartesian equation. So always when you have something that is not sine, cosine, or things that you have never seen before, one very helpful way to check it out is to put it into Cartesian equation. Now if we do the same thing for the next questions, I guess that's gonna also shorten our answer a lot. So it's gonna be cosine theta over sine square theta. And so this case, there's one little trick that you should do. So you have r sine square theta equal cosine theta. Or in other words, you have r square sine square theta is equal r cosine. As you can see, if I multiply both sides of the equation by r, this thing is going to give me y squared, and this thing is going to give me x. And so again, this drawing is really easy, right? X equal y squared. Or you can just write at that. But you wouldn't be able to figure this thing out, right? So again, try to, if you know, one of another hint is that if you cover the left side, it's going to give you just cosine on the other side, and you know that if you need x, you need r cosine. That's kind of like one of the way that I figure out how I'm going to multiply one or the r. And so that's example 3. Let's go to 10.4. So 10.4 is area in polar coordinates. So kind of like it gives us a way of how to find, say if you have a graph like this. And so you want to find this area only from when you sweep through angle theta 1 to theta 2. So this is the way that you're going to find it. So it comes from the fact that an area of a sector of a circle is a equal half r squared theta. And this is also coming from like the a of full circle is pi r squared, which is half of 2 pi, which is the angle of that r squared. Now, if you have a region bounded by r equal f theta, r equal g theta, like these two curves, and it's bounded by theta 1 and theta 2, or alpha and beta, then the area of that region is going to be half of the integral from alpha to beta f squared minus g squared d theta as well. And so the way that you're going to do it, graph the curves. If you're asked to find an area of a region bounded by two curves, graph it out, use symmetry, special case. Some of the special case is much easier. Maybe you don't have g thought, maybe you don't have g theta. G theta is going to be 0, or you can use symmetry. Say, if you know f theta is even r, you can either cancel it out, or you can put it into kind of like simplify your calculations. So and that can also be done. This symmetry can easily be used by graphing the curve as well. So before I go to the example, there's something I want you guys to see, and I think it's a very helpful app for this class, because it gives you the chance to kind of like check back your work when you are dealing with some strange coordinates. Okay, let's go to so I'll share the screen on. So if you look at this, a website that I always use, I think I may have introduced this to someone else before, but just a thing like this also work with this one also work with polar coordinates, so kind of like some helpful thing, isn't it? It come handy in the place that you need it. So this is gonna be what I use for this class so far to figure out the code, because I really don't want to write it, but I can screenshot in to Zoom later for you guys. So I'll stop sharing this and let's go back to our slide. So set up but do not evaluate the area of the region R inside that. So let me draw two curves into it before we start doing it. So let's bring screen there. Okay, give me a second. Crop it so that is helpful, and you guys can follow what I'm saying in this thing. Damn. Shame is can be easy. Can be better post, right? So this is what we have, but we can avoid this and this. So let's back to this. So here, set up but do not evaluate the area of a region inside this curve and outside of that. So here we have the area inside curve R but outside of that. So is this going to be this area inside of that, outside of this area, and also this area? In other words, you need to find the area of these three, and if you notice, they're all symmetry, and those three areas definitely equal to one another. So if you just find one, you should be able to find the other one. Now, we're looking for each of them. So you have area that we need to find is 3 times 8 of one loop, right? Minus 8 of half. So it's kind of like the area of this curve minus the area of the radius inside. And so the way we're gonna do is that let's see what is the angle from here to here. So the angle of a loop when it crossed it is when you have sine 3 theta equal half. And so I think I put the wrong graph here anyway, so we're gonna redo it. So this is where we're gonna solve for that. So we have 3 theta is going to equal, what side is gonna give you half? The value of sine is gonna give you half, and you don't need to think of all values that are gonna give it. It just should be in just the first quadrant. And so 3 theta is most likely to equal pi over 6 or pi over, or if it's on this side, it's going to be 5 pi over 6, but that's a little bit too much. 5 pi over 6. Then you're gonna have theta equal pi over 18 or 5 pi over 18. But pi over 18 is what I'm looking for here. 5 pi over 18, it might have already gone down here. And so in that case, you have pi over 18 is this, and then 5 pi over, sorry, I kind of like make a mistake, mess up this thing a little bit. So the way that these two intersection is fine is, yeah, the two first point that they actually cross one another. And so after having that, now we can set the area that we need to. So it's 3 times from pi over 18 to 5 pi over 18 of the outer radius, which is f squared pi. Do we need pi? Yeah, we don't have pi, but we multiply half, and then f squared, which is going to be sine squared 3 theta minus 1/4, because one is half square d theta. Or you can even use further symmetry. So if you look at here, this line is this big area of one loop outside of the particle half radius is, you have the symmetry along this line, right? And you have to figure out what is the middle angle between pi over 18 and 5 pi over 18, which you can do by add them together and find what is the average, which is going to be this one. So it's going to be 5 pi over 6 pi over 18 divided by 2, 6 pi over 36. So yeah, it's 5 pi over 6. Therefore, we can even go further, put it as from pi over 18 to pi over 6 sine square 3 theta minus 1/4. This is the 1/2 disappear because now I replace it with because this one, like, I'll write out a step and half, multiply half from pi over 18 to pi over 6 sine square 3 theta minus half d theta. Yeah, the graph here should not have this, but I'll change it after we finish the sessions. But yeah, that's what we're looking for. It's this. So again, I would say when you graph the curve out on one platform, that'll be very easy. That's considered, that's when your graph is correct. Let's do the next one. So find the area enclosed by a loop of R equal. So again, the graph is gonna look like yes, not doesn't look that nice. So kind of like that, and then area enclosed by one of these loops. So we know the fact that when you go starting from 0, you go all the way to here, the farthest point at pi over 6, and you come back here at pi over 3. come back to 0 at pi over 3. Therefore, one loop of it is going to be enclosed from 0 to pi over 3. So that area is going to be half of 0 pi over 3 sine square 3 theta d theta. Or another way you can do it, again, I would say find that symmetry is going to give you from 0 to pi over 6. This half cancel out with the 2 sine square 3 theta d theta. So pretty easy, isn't it? As long as you get a graph, I feel like you guys can figure this one out pretty easy. Last example, set up but do not evaluate the area of a region inside both curve and this curve. Now this is where it's gonna come a little different, and it doesn't touch on the sine 3 theta graph that we've been using since the beginning of today. So we're gonna actually have the graph what is 1 plus cosine theta and 1 plus sine theta. And I think it's not hard because I've seen that in your lecture notes. So you guys should be able to figure it out pretty quickly, but still we're gonna graph it. So I remember this graph is something like a heart shape before. So this is the area, but which one is which, we need some trials. Let's see, when you have r equal when you have r equal 1 plus sine theta and r equal 1 plus cosine theta. So when you have, see, say for the upper curve, theta is when theta equals 0, you have r equal to 1. And so when theta equal pi over 2, you have r equal to 2. So this curve is r equal 1 plus sine theta, and this curve is r equal 1 plus cosine theta. And so the curve inside both regions is this region. And so we have to find that. And to find that, we have to find what is the boundary and how they get to one another. That's how we're going to solve this. To find the intersection, like the two boundary of theta that we need to use, that's going to give us sine theta equal cosine theta. Or you have tangent theta equal 1. Let's consider both of them are different than 0, and that's what happened. So when you have this tangent, it's going to be at pi over 4, or it's going to be 5 pi over 4. Both of them have to be positive at the same time. So basically we're saying the first point that they cut is pi over 4, and the second point that they cut is 5 pi over 4. So you start here for sine and you start here for cosine. So they all go to pi over 4 at this point, and then they all go down to this point of 5 pi over 4. So they cut at these two. Therefore, the area, and I mean my drawing is kind of skewed, but you should be able to see that there's the symmetric over here. So your area is going to be from first it's from 0 to let's see, it's actually just use a symmetry. So it's from pi over 4 to 5 pi over 4, because you already use a half over there. The outside curve minus the inner curve. So say, what is the outside curve from pi over 4 to 5 pi over 4? Outside curve is sine. Oh, actually you only care about this region, bounded by cosine from pi over 4 to 5 pi over 4. So it's going to be cosine theta plus 1 square d theta. Or if you want to find the one that's by psi, then the way that you're going to do this is you can set up the other one. So, but the other one is gonna start not from 5 pi over 4 to pi over 4, but it had to go from a smaller angle. So you remember our angle is going to equal negative 3 pi over 4. And so this one is going to give us, is going from negative 3 pi over 4 to pi over 4, 1 plus sine theta square d theta. And so this curve is, yeah, so that should be clear now of the way how we're gonna do it. So if you don't have any questions, so that's all I have for today. And we also have the practice problems, so don't forget to do them. And if you have any questions, please feel free to let me know. I'll try my best to rearrange, like put another graph up there and maybe put a better graph down here. But you can always go to the website I show you and figure it out, right? So that's all I have for today, and I'll see you guys next week in the final exam review. Have a great weekend, guys.